Okay, so first I would like to thank the organizers for inviting me to this really nice meeting. So I'm not really in this uh, very complicated area, but it's really been a very nice learning experience for me. Uh, so yeah, I'm really grateful to the organizers, and so I'll try. So this, I mean, talk. I'll try to make some connections with cold atoms, maybe. Okay, so this is work done with a postdoc at ICTS, Madhumita Saha, Atharva Naik, graduate student at ICTS, Manas, who is here, and I hope they're also there, and David Hughes from Princeton. Okay, so so I just want to say that these two people are really the main players in this work. I mean, they have done some just playing around with the system. It's a very simple system, but just playing around with the system, they discovered a number of beautiful results, and so there's some nice stuff which has come out from this. Okay, so I'll talk about hydrodynamic description of dynamics of entanglement in a freely expanding fermionic gas. So it's just I take some bunch of non-interacting fermions in a box, and I let it. I open the box so the fermions are escaping, and I look at the entanglement between the fermions in the box and the environment. Right. That's the basic problem. And we try to understand it using sort of hydrodynamics, which is the kind of nice thing. Okay, so there are two parts of the talk. One is this is what published in a couple of years back, and here basically we look at this a simple toy model, the same setup, but it's a toy model which tries to reproduce some aspects of this so-called page curve, which is known in black hole, like in the context of black hole evaporation and the information paradox. Okay, so I'll briefly explain what this paradox is. So the setup is again exactly this. You have, let's say, fermions at, let's say, 0 temperature in a box, and you let it expand. Okay. And I'll present results from exact microscopic numerical calculations and from a sort of generalized hydrodynamic theory. And what we'll see is that there's really great agreement between these two. And what we'll show is that if you look at the entanglement entropy, it follows this so-called page curve, which I'll explain in a while. If you look at the entropy of the radiation, you find that it keeps increasing. Okay? So this is similar to what is known in black holes. Okay, and then I'll talk about the same setup, but at finite temperature. So instead of starting from a 0 temperature state, I start from a finite temperature mixed state. And then again, ask the same question: how does the entanglement, how does the entropy change with time? And we'll show that you can again compute this using a very simple semi-classical wave packet picture. Okay, so okay, so I'll present some results on this dynamics of eigenvalues of correlation function. Okay, so one of the motivations is that entanglement is one of the important measures of quantumness, and understanding entanglement even in a non-interacting many-body system is kind of interesting, and already as I'll show that it's quite non-trivial. Okay, and I'll also discuss some possibilities for experiments in cold atoms. Okay, so this is the black hole information loss paradox. So imagine you have a black hole which is in a pure state, right? So somehow you have some cloud of gases which attract and then form a black hole, which I can imagine it's in a pure state. And then what Hawking said is that black holes radiate, and they radiate completely thermal radiation. So eventually the black hole is shrinking, and eventually it evaporates completely into a pure thermal state. Okay. So you have a pure state goes into a mixed state, and that's kind of the paradox. Like, where is the information about the pure state gone? And one way to state it is by looking at the entanglement entropy. And so what Hawking computed is like you have the black hole and there's radiation coming out. And he did a semi-classical calculation for the entropy of the radiation. Okay, and this is what he found, that this entropy keeps increasing. Okay, so the radiation entropy, keeps increasing with time. Then there was a famous calculation by Page in 1993, where he basically argued that the entanglement between the entropy between the black hole and the radiation, initially it will go up because, as things go out, they get entangled. But eventually, after like maybe half of the Hilbert space of the black hole has escaped, the entanglement has to go down. Okay, so the Page curve is the entangled entropy as a function of time. It has to go up, and eventually it reaches some what is known as the Page time, after which it has to go down. Okay, so there's a very simple argument why. At some point the entropy has to go down. Okay, so there seems some contradiction between the fact that Hawking's calculation shows that the entropy of the radiation keeps increasing, while here one finds that it has to go down. Okay, so let me just talk about some earlier work on entanglement in 1D free fermion systems. So there's a lot of work on the static problem. Like I just take a ground state of like a Fermi gas in a ground state, and I ask what's the entanglement between two halves, right? Or like of subsystem of size L and the remainder. And there's a lot of work, and as you increase, it might either grow logarithmically with system size for low energy states. For high energy states, it grows linearly with length. So these are known as area laws and volume laws. So these are static problems. For dynamics, what was studied is like two kinds of initial conditions. So let's say something is known as the domain wall initial condition, where you imagine on the infinite line, you have on the left half, it's fully filled with fermions, and on the right, it's completely empty. Okay, so this is like a domain wall. And then you ask what's the entanglement between these two halves. Okay, or you can start with some, let's say, like a homogeneous initial condition, but you then suddenly change the Hamiltonian, and then the system evolves and you ask like entanglement between two halves. Okay, so both these setups have been studied, and some of the, like one of the earliest work was this work of Calabresi and Cardi, and then there's a lot of other work. And some of the interesting findings are, let's say if you're looking at this domain wall initial condition, then if you start with a low entropy state, then you find that the entropy increases as logarithmically with time. Okay. On the other hand, if you start with a high entropy initial state, it grows linearly with time. So this is like for a perfectly homogeneous system. Okay. Then if you make a small change, like on the infinite lattice, let's say you just put a defect at one side and look at the entanglement between this half and the other half, then this log t changes from, so the entanglement growth changes from log t to linear in time. Okay. So this, a small change can change things completely, like very drastically. Okay, so this linear growth has been understood from generalized hydrodynamics, and this is what I will also talk about. And while this logarithmic growth in entanglement has been understood using something called fluctuating quantum hydrodynamics. Okay, so just to make this connection with cold atoms, I just want to point out this very interesting experiment from this group of Lukin, which is looking at entanglement growth in many-body localized systems. So it's an MBL system, and the setup is, it's I think, basically rubidium atoms, and somehow you can get a 1D lattice. And so the model is just Bose-Hubbard with disorder. So it's a 1D Bose-Hubbard lattice with disorder, and you basically start with some coincident initial condition where every site has one atom, and then you let the system evolve, and you compute various things. One of the things they computed is just this, the entanglement entropy at one site with the rest of the system. Okay, and this they've like experimentally this was measured, this how this entanglement entropy grows with time. So in this case, it grows. There's some growth, and then there's a saturation because the system equilibrates, right? Because it's a finite system, it eventually will equilibrate, and this is what you find. Okay, so this paper has some nice discussions of like the entanglement entropy can be divided into two parts. One which is related to number fluctuations, and the other which is related to like fluctuations in the configuration of particles. Okay, and you can kind of measure both in the experiment. Okay, so this is some aspects which I think our work also kind of brings out. And so this is of course done in a more complicated setup, but I can imagine that many of this setup is easy to realize for the case that I'll discuss. Okay, so now let's discuss the model that we study. So it's just a 1D lattice. This is the Hamiltonian, just hopping with some hopping element G at every site. So this is what I'll call the system, and this is what I'll call the reservoir, right? So everywhere it's the same, except at the junction between the system and the reservoir, there's some. This is what I'll call a defect. Okay, so this coupling GC is different from what the coupling here, and then we also put some on-site potentials at these two sites. Okay, so that's the only inhomogeneity in this system. Everywhere it's completely just given by this hopping Hamiltonian. Okay, so I mean I'll discuss various kind of defects, and one particularly simple defect that we studied. Okay, so here basically, okay, and the initial condition is, like I said, you fill all these lattice sites with exactly one particle, and this is completely empty. Okay, and so this is the connection to black holes. This is like the black hole, and this is the environment, and you're just escaping. Okay, so I just want to explain like the kind of defect that we can put here. You can put the various possibilities are there. Depending on what we put for the on-site potentials and this coupling. Okay, so one particular choice, you can put these couplings in some special way, such that if you look at the transmission coefficient of electrons going from left to right, let's say, which I call Tk, then it becomes completely independent of the wave number. Okay, so all wave numbers transmit with the same transmission coefficient. So this is called a conformal defect, and I'll mostly present results for this case. Okay, so this is transmission coefficient versus K for different kinds of defects that we studied. So for the conformal defect, it's completely independent of K. Okay, so the idea of a defect is that basically every time an electron comes, it kind of gets split into two, and so that creates the entanglement. Okay, so if I didn't have a defect, like I said earlier, the entanglement would grow logarithmically with time. But with a defect, it grows linearly because this defect, in some sense, generates entanglement. Okay, so now in general, of course, entanglement is something very difficult to compute even numerically. But for non-interacting systems, it's kind of simplifies. And basically, okay, non-interacting, and if we are looking at Gaussian states. Okay, so Gaussian states are like, for example, a Slater determinant, or any state where 2-point correlations contain all information about the state. Okay, so we always look at such states, and in this case, I mean, basically you can compute all properties of the system just from the 2-point correlation function, which is defined like this. Okay, so this is the many-body state, and then you just compute this correlation. Okay, so this, I mean, it's a single particle object, and you can evolve it numerically very efficiently. And once you have this correlation matrix, all physical properties are easy to determine. For example, the density is just given by the diagonal elements of the correlation matrix. And then you can study things like number fluctuations and so on. Everything is contained in this. Okay, so now, of course, what we are interested in is the entanglement entropy, and that is given basically by also from this correlation matrix. And the idea is that, okay, so for the entanglement entropy, one has to, let's say, I have to find the reduced density matrix in the system, of the system. And from that, we have to just take a trace rho A log rho A, and that gives the entanglement entropy. Now, for Gaussian states, I mean, the reduced density matrix always has this form, and where this D matrix is given just by the, if you know the correlation matrix, then you completely know the reduced density matrix. Okay, so basically, one has to look at the correlation matrix restricted on the system or on the reservoir. And from this correlation matrix, if one finds eigenvalues, then the entanglement entropy is completely given in terms of these eigenvalues by this formula. So this is a very nice thing one can do for non-interacting systems in Gaussian states. And okay, so this is the formula that we'll use a lot. Okay, any questions? Okay, so now, so this is, yeah. Yeah. Okay, so this is of course a non-equilibrium, I mean, evolution. So, so entanglement entropy is defined exactly this way, right? So I don't know what was your question. I mean, I didn't get it quite. Sorry.
How to quantify the entanglement by using the entropy when we have already a fermions in already filled state, and the filled state will fermion transfer to the empty state.
Yeah.
So how to change the entropy and how to quantify the entanglement? And what is the entropy
okay, no, I mean, see, this is my system, right? Okay, so I have I mean, this is my system which is completely full, and then I open this wall, and this is evolving, right? So I mean, it will after some time, if you look at the density, so there's some electrons have leaked into the reservoir. Okay, and I'm computing entanglement between this and this. Okay, and the entanglement to compute is like, okay, I have a pure state psi, and from this I construct the density matrix, which is, let's say, psi, right? This is for the full thing. And then I find the reduced density matrix in the system, and from that, you just take trace rho A log rho A, that gives the entanglement entropy. Okay, so that's the formula.
Basically, we take a fermion. What is phenomena change when we use the bosons?
I mean, you can do the same thing for bosons also.
Bosons also.
Right, yeah.
Okay, thank you.
Okay, so so this is the microscopic prescription. Now, what's the hydrodynamic theory? Okay, so in hydrodynamics, you basically think of the electrons as a gas of quasi-particles, but you need to think of them as localized both in position and momentum. Okay, around some, let's say, x and k, and there's some spread of order h bar. And let's say their phase, so we are talking of phase space, and there's some phase space density, which is, let's say, I denote by this. And these quasi-particles have a drift velocity, which is given by their basically the group velocity. So for this electrons, I have some spectrum, and because it's a lattice lattice fermions, the spectrum in this case is just minus of cosine k for the parameters I chose. And so the group velocity is the sine k, right? So, so I have these localized particles which are moving with some group velocity, and then because they're non-interacting, you can simply write a Euler equation or which looks like this. Okay, so they just drift with constant velocity. Okay, so this is roughly like you can think of it like a Boltzmann or kinetic theory equation with no collision terms, and this is also the simplest example of what is known as generalized hydrodynamics. Okay. So more formally, you can actually derive this from a Wigner equation. So let's say you have this many-body wave function. From this, you can construct a single particle density matrix, which is basically the coordination function. And from this, you can there's a prescription to construct something called a Wigner function, which is a function of phase space. And then if you take this Wigner function and do a bit of coarse graining over some h bar scale, then you would essentially get this classical sort of phase space density. Okay, so this is what we do. And then one can show that to leading order in h bar, this n satisfies this equation. Okay, so the simple place to look at it is this review article. Okay, so now we have the semi-classical description of the electrons. And from this, okay, so once we know the phase space density, we can compute things like densities. Of course, you just integrate over k. And how do you compute entropy? Okay, so there's a sort of formula which was first proposed by Yang, which is basically you take this phase space density, And so just imagine that locally, I mean, like you have some Fermi distribution, right? So this phase space density is like a local Fermi distribution. And then if I ask what's the local Boltzmann entropy, then it's just n log n plus 1 minus n log 1 minus n integrated over k, right? So it's the local Boltzmann entropy in any place. So I can define this from my hydrodynamic theory. And okay, so now right now it's not clear why this should be related to entanglement, but this is some entropy. And this has been studied in relation, trying to understand entanglement entropy in earlier work. Okay, and this is what we'll use. Okay, so now given this local entropy density, I can compute, integrate this in the system part, and this is what I'll call the hydrodynamic entropy of the system. And I can also compute it in the reservoir by just integrating over the reservoir x, and I'll get a system entropy for the reservoir. Okay, so this is what I can do from hydrodynamics. Okay, so now only thing we need to figure out is like given this initial condition, how does n evolve with time? Okay, so in phase space, if I look at the phase space distribution, so let's say in phase space this is k and this is x. So this is the origin. So initially the momentum we have like it's completely filled from let's say 0 to pi. So k goes from 0 to pi. It's a fully filled lattice, and from let's say minus n to 0, right? So this is completely filled. So this is my initial phase space density, and now when I open this, it's going to evolve in some way, right? Okay. So with time, this is what we need to solve. So we have to solve this equation, but there are some boundary conditions. There's a wall at the left, and there's a defect out here. Okay, so I mean, what the defect does is like every time, I mean, you should think in the kind of semi-classical picture. A wave packet comes with some probability it transmits, and that would be just the transmission coefficient Tk, and with some probability it reflects, right? Okay, so and then this phase space density is just built up by adding all such processes where things can transmit with some probability and reflect with some probability, and then there's a wall where again it gets reflected. Okay, so we'll write the solution of this equation. So I just want to show you what the phase space, how it evolves in phase space. So initially it's distributed, let's say, in this minus pi to pi. And then things like these are all these are positive movers, all these are negative movers. So the positive movers move into this half, but they also get reflected and then they fill up this part. Okay, and this with time, this in phase space it keeps spreading. Okay, so yeah.
That equation written for the
entire line.
Entire
yeah.
long. Infinitely long.
Yeah, I mean, this is for a homogeneous thing, right? Yeah.
So, take like this.
Yeah.
The reservoirs, doesn't that get modified?
I mean, so I just treat it as a boundary condition, like where, okay, yeah. So I think of the particle picture. I mean, because this equation, I can interpret it in a particle, I can just write semi-classical equations of motion, right? And then I just think of the particle picture. Okay, so I mean, if there was no defect and on the infinite line, the solution of this equation would just be this. Okay, so I mean, you can just imagine every particle like is boosted with some speed, and it would just evolve in this. So I can write this equation solution very easily. Okay, but now I just have to take into account that there are these multiple reflections, and then you can kind of write down a solution like this, which basically takes account of S reflections at this interface. Okay, so this is the density on the phase space density on the inside the reservoir, and S is just the number of times it kind of reflects back and forth, and then it transmits. So, but it can only transmit once because there's nothing to get reflected. So that's how you get this factor, and otherwise we just sum up all the possibilities. Okay, so that's how you get this solution. Okay, so now given this solution, we know how to compute, let's say, the density profile and the entropy. So this is results for the density profile, and the points here are the results from exact numerics, and the solid lines are from the hydrodynamic theory. Okay, so at t equal to 0, it was something like it was 1 and 0 here. And then with time, the density, okay, there's this kind of funny thing at the jump at the boundary. But you can see that the hydrodynamic theory kind of reproduces the exact numerics extremely well, right? And this is the current, which is the current of particles just at the junction. And what we find is that it kind of remains constant till some time and then starts decaying. Okay, so I mean, so it's easy to understand like what is this time after which things starts changing. It's basically like if you have a box and you ask like if you look at the fastest particle, how long does it take to realize that it's a finite box? Okay, so that will be like twice the size of the box divided by the Fermi velocity, and that's this time scale. Okay, so that it's a simple time scale. So and this we'll see is actually gives what gives the 25 the page time. Okay, so right, yeah. So now let's look at the entropy. And this is the entanglement entropy versus time. So I'm plotting here three things. One is the exact entanglement entropy, and this is of course the same for the system and the reservoir, and that is this blue circles. And then from the hydrodynamic theory, we said that we can compute either the entropy of the system or the reservoir. So this is for the system. This is the green line, yeah, which you can see follows the entanglement entropy extremely well. While for the radiation, this is the entropy, and at early times it follows the entanglement, but at late times it keeps increasing. Okay. So, I mean, okay, so this I would say is very similar to what is seen in the black hole evaporation. If you look at the entropy of the reservoir, it keeps increasing, but if you look at the entanglement entropy, it actually just follows what is expected of the page curve. Okay, so this is our page curve, and this page time here is very simple. It's just the time for the system to realize that it's finite. Okay, so I mean, so the other interesting features are that this at early times less than the page time, this growth is linear in time, and at late times there's a power law decay, and all this can be computed exactly from the hydrodynamic theory. Okay, so including the prefactors and so on. So this everything can be computed exactly. Okay, so the other interesting thing is looking at number fluctuation. So I can just ask like at some time if I measure how many particles have escaped. So of course it depends. Every time I measure, I'll find a different number. So what is the distribution of this number of particles which has escaped? Okay, so that's the full counting statistics. And one can write a generating function for this number distribution. And for this non-interacting systems, everything is again given exactly in terms of this eigenvalues of the correlation matrix. And so recall that the entanglement entropy was also given in terms of the same eigenvalues. And because they are both related to the same eigenvalues, you can actually find an exact relation between the entanglement entropy and number fluctuations. Okay. So this is, I mean, so an entanglement itself is difficult to measure, but then using noise, you can actually say something about the entanglement. Okay, so this is the idea of this in this paper. Okay, so in our setup, we also measured the number fluctuations, and let me talk about this now. Okay, so I also want to mention that at large times, this generating function has this large deviation form. Where this mu of lambda is given by this sort of nice formula, which is called the Levitov-Lesovik formula for full counting statistics. And this is also something that we can derive very easily from the semi-classical approach. Okay, so now let me show some of our numerical results for this number fluctuations. So like I said, there's this exact relation between entanglement and number fluctuations. So if we just plot the second cumulant in our setup, which is this number of just n square minus n average square. that is given by this blue line. Okay, so this is the entanglement entropy. So you can see they are kind of quite close. Of course, this depends on all cumulants, but actually the second cumulant itself is quite often already very close to the entanglement entropy. Okay. So here I have put some, there are some prefactors that appear in this formula which we have added here just to get them closer. Okay, so now I'll go to the second part, which is results for finite temperature initial states. So this is kind of ongoing work. Okay, so I mean, here one of the main things was that, I mean, if I look at the system hydrodynamic entropy, it agrees with the entanglement entropy at all times. But if I look at the bath entropy from hydrodynamics, that kind of deviates after the page time. Okay. So now what I'll show is that we can, we'll look at finite temperature mixed states, and we'll propose a modification of this entropy formula, which will actually reproduce even after the page time the entropy of the reservoir. Okay. So this is kind of a really interesting result. Okay, for 4 minutes. Okay, I think that should be enough. Okay, so first, I mean, at finite temperatures, one can do two things. One can take, like, I can choose my pure state from an ensemble, from a thermal ensemble. I can evolve it and compute entropy, and then I can take an average over all states, right? That's one possibility. The other possibility is I could just start with a mixed state and evolve it and just compute von Neumann entropy. Okay, so these two things will give different results. And what we can compute from hydrodynamics is the second case. Okay, so here I show results for at temperature 1. Okay, so the plots, this curve here is the entanglement entropy really, which is done using this procedure. So I'm at some temperature beta 1, and I think chemical potential also 1. And then you choose some pure state, and then compute the entanglement evolution and do an average over all pure states. Okay, then of course you get this page curve. If you start from a mixed state, then you can imagine that even at time 0, it should have a finite entropy. So in that case, you get a curve which looks like this. Okay, so this is for a mixed state. If I just compute the von Neumann entropy of the system, then it starts from some high entropy because it's at high temperatures, and then it goes down as the system evolves. For the environment, it has initially there's nothing, so it's always at very low entropy, and then it increases and evolves in some way. Okay. Now, and in this case, I mean, so in our earlier calculation, what we saw was that the environment entropy, I mean, actually went something like this. It never agreed with hydrodynamics, but here I show the new formula that I'll use, which is this green curve. And in this case, you can get exact, like very accurate agreement with the numerics, even for the environment entropy and also for the system entropy. Okay, so these are the two results that I'll now derive. Okay, so since there's not much time, I'll just quickly go to the basically this modified Yang-Yang formula. Okay, so the idea is completely using a semi-classical picture. Okay, so maybe let me go to the next page. Okay, so yeah, so the basic idea is like, so we have this phase space density, or let's say on this right hand side. So at any time we can compute the phase space density everywhere, right? And to find the entropy, what we did is we integrated the in this region. But now what we'll do is like we compute a modified phase space density, which kind of adds all this like all these sections and brings them. So let's say this is 0 to 2n, and this is 2n to 4n. So I'll add all these phase space densities and put them together at 0 to 2n. Okay, so this part 4n to 6n, everything I'll put them at the same place. And so this is this summation. and then using this object, we compute the entropy. Okay. So with this change, somehow it works quite amazingly. Everything it matches with the numerics perfectly. And I'll try to explain why this works. Okay, that's what we'll do. Okay. So before that, I'll just show some results from, like, if I just look at the eigenvalues, what do they do? So these are the eigenvalues of the correlation matrix. I mean, let's say at zero temperature. So initially everything, like I start with 1, 1, 1 diagonal. I'll just take 2 minutes.
Yeah, sure.
Okay, so everything starts 1, 1, 1 because I have a fully filled Fermi sea. And then what you see is that you get some extra eigenvalues keep popping up. And these values, so this is in the system, okay. So these values of that you observe is exactly related to the reflection coefficient, okay. So this value is, for example, exactly Rk, which is the reflection coefficient. This is R square, this is R cube, and so on. Okay, so this is the one of the ideas. And if you look at in the reservoir, you see a similar thing. Initially, everything is zero. There are no particles, so all eigenvalues are zero. And then you get some eigenvalues at a value which is proportional to T of k, which is the transmission coefficient. And then you get some eigenvalues which is proportional to T of k into Rk, because it's like eigenvalues have reflected once and come. And this is proportional to Rk square into Tk and so on. Okay. So using this observation, I mean, the hydrodynamic theory is based on this. So basically, let me just quickly explain the argument. So the correlation matrix, because we have non-interacting particles, is basically given by this object. So phi alpha xt is like my initial wave function. I just let it evolve, and let's say at time t it looks like this. Then this is basically the correlation matrix. Okay, this is exact. I mean, alternatively, one can show that you can the eigenvalues can also be obtained by looking at this matrix, which is just using a different basis. And okay, so this is one idea. And then the main idea is that we'll choose a very special basis, which is the wave packet basis. Okay. So the wave packet basis is like, I mean, I can either choose plane waves, which is the momentum basis, or position-based eigenstates. But if I choose a basis where every particle is like localized in some small cell in phase space, then in that basis, the dynamics becomes very simple. Okay. So basically, if you look at if you form these wave packets, what you will find is that, okay, so the wave packets can be in different places in phase space, right? I mean, but if you take any of these wave packets, then after some time you'll find that if it's a small velocity wave packet, then after some time it looks like this. Okay, so some part remains within the box and some part has gone out of the box. This is another sort of a high momentum wave packet, which has undergone several reflections and now can be found in different places. Okay, in the system, of course, there's always one wave packet. But in the reservoir, because there are a number of reflections, this just corresponds to a different number of reflections, okay? But these are still localized, okay? And that's the main idea. So at all times, they are kind of orthogonal. And using this picture, I mean, basically in this phase space picture, if you construct the correlation matrix, then you can pretty much compute the eigenvalues of the correlation matrix exactly. And this is what gives this formula. Okay, so okay, yeah. So this again, using this modified hydrodynamic theory. This is a comparison of the exact microscopics and the hydrodynamic theory predictions for the second cumulant, and this is the third and fourth cumulants. So you can see there's really fantastic agreement with the hydrodynamics and exact numerics. Okay, so I'll just stop here.
Let's thank the speaker. We have time for a couple of quick questions. Yeah.
I have a question. Sir, basically you give a theory for hydrodynamic state.
Yeah.
We can apply for the same theory in cold atomic system or Bose-Einstein conditions.
I mean, there's of course hydrodynamics for cold atom systems that is there. Or only question is like, can you? I would imagine some of this would work. Yeah. I mean, like how?
Because I'm working in cold atom system.
Yeah.
I'm really impressed by your theory. So this is my genuine question: how can we implement this theory in cold atomic system? If it is any possibility to implement this theory, and what is the application for this theory in cold atomic system?
Okay, I mean, see, like my thing was non-interacting fermions, and which you can of course realize in cold atoms. I imagine not maybe if you can do fermions, it's more difficult. And but with interactions, I mean, if it will change a bit, but I mean, you can in principle it's all directly applicable, right? I mean, everything is if you can realize this in an experiment, which might be difficult. With interactions, maybe if it's weak, I mean, they shouldn't change too much.
Okay. Okay, sir. Thank you.
So you started by motivating it through by black holes and information loss paradox and stuff like that. The point is that inside the black hole we have a mush. We do not know what that mush is. Okay, yeah. And what is? I mean, so far as my understanding is that what is the black hole when it loses its mass, it's losing it via emission of light of some form or the other.
Right. Yeah.
So you basically wanted to get to this page entropy entropy of entanglement entropy, but the question is, why did you pick this analogy? I mean, I'm not sure whether this analogy is the right analogy. I understand that you want a page the page curve,
right? Yeah.
But aren't there other systems which have this entanglement entropy like described by the page curve? Because it's not clear that you have a pure state and whatnot in the black hole or whatever it is. I mean, we don't know.
Okay. So first of all, for the black hole, I mean, the earlier difficulty was you don't have really a quantum theory of gravity and so on, right? But recently, actually, there has been, and people have done calculations. And this, I mean, at least some people think that this paradox is now resolved. I mean, you can get this page curve from a completely quantum calculation, okay, using like, I mean, of course, string theory models. So, I mean, but the idea here is like, it's a toy model which has the same features. And in particular, the fact that if you look at I mean, it also points out that it's important to be clear about what entropies one is talking about. Right, because entropy is kind of tricky. I mean, like Boltzmann entropy versus entanglement entropy. I mean, so in this calculation also, when you do semi-classical calculations, you can get something which are very different from completely microscopic, right? So these are some things that this calculation points out, and and it's the simplest toy model which reproduces the page curve, plus the fact that you have a Boltzmann entropy which keeps increasing.
Okay, maybe later you guys can discuss. In the interest of time, we should move on. So, let's thank the speaker.